So good evening and welcome to the additional interactive session of the fabrication techniques for MEMS-based sensors, clinical perspective. I am Vikas Pandey from IIT Jodhpur. This is brief about me and this is our last class for this session. Yeah. So yeah, first thing that last time we were discussing about, are you able to hear me?
Yes, sir.
Yeah, we were discussing about STL format. It is not soft lithography. It is related to stereolithography, this term.
Okay.
And
Stereo. Okay.
yeah, stereolithography is something like where you can, this is a software, CAD software that was originally the one that used the STL format. So it is very commonly even related to that stereolithography term. Though it uses triangles to create the structure, that is why it is generally known as standard triangle language or standard tessellation language. Okay, because each file is made up of series of linked triangles that describes the geometry. Uh, it's not moving. Yeah. So how to identify a STL format or how is it different? First, it is a 3D structure. So will have STL file format. And the thing is that it will have no colors. Like if you see these two structures, there is no color information. Just the structure information is there. So STL is used for the like why is STL preferred? Like I discussed in the previous class also, right? OBJ, and there are other file formats also which can be used to create the 3D model. But STL is the preferred one because it does not carry any extra information which is not required for the 3D printer. Fine.
Yes, sir.
So it is not soft lithography, it is stereolithography. That is the term.
Yeah,
That is,
stereolithography. Yes.
yeah. And this is actually the first software, like who developed this? Chuck Hall, I think. Yeah, Chuck Hall developed this 3D printing. So he made this stereolithography CAD. And there this STL file was used. And that is why people generally refer it to stereolithography also. Fine. Okay. Next is the etching process. Like we discussed that we will be talking about etching and isotropy and these things, right?
Yes, sir.
Okay. So just a basic revision. Today is like revision class only. Okay. So etching is the process by which we remove the material from substrate or of thin film or surface. Okay. So there are fundamentally two types of etching. Wet etching, in which we have liquid based etchant, where we dip the wafer and there the etching occurs. The second type is dry etching, which is mostly plasma based etching. But there are other dry etching processes also. Okay, plasma etching is the most common one. So, what are the parameters when we talk about etching? It is one of the very important step in all our fabrication process. The reason being that it will define the structures we make. Like if we have done good etching, we can get a very good aspect ratio. And if we are not get like if we wanted such structures, even though we have done all other steps fine, and if etching is not proper, we might get something like this, and whole structure will be damaged. Or if it is something like this, and this, then the upper portion will get removed. Fine. So there are some parameters that is used to define the etching process, or also known as etching metrics. One of them is bias. Bias is the difference in the lateral dimension between, you can say, what was expected. That is that suppose this is a uh, this is our wafer. On it we made a pattern like this. Okay. So this is what we expected. This is the mask we made. But later on, when we did the etching and everything, we found that there is some difference. difference from the etched image and the mask, that is what the pattern was there. That is called as bias. The second one very important parameter is the etch rate, the rate at which the etching will happen. If it is very slow, then we will have to give more time. If it is very fast, we can do it very fast, but if we keep it for more time, it will remove some extra material which is not required, right? So optimal etch rate is important. Then is selectivity. When we are going for etching, it is very important that it is selective towards the material that we want to etch. It should not remove other materials, right? So it is ratio of etch rate of one material over the other. Okay. For example, the selectivity in ratio of etch rate of layer being etched to the etch rate of the mask or layer under. So, like suppose we are making a putting a mask here, okay, and this is the layer we want to remove. This one, okay, and then below it we have silicon, and this is say SiO2. Okay, generally it is not SiO2. Uh, it can be other film also. Like let's say it is ZNO or gold. For example, we put gold. Okay. So what will we expect if we want to etch it? The etchant should be selective to which thing? Gold. Uh, it should it remove gold only, or should it remove gold as well as photoresist as well as silicon? What should be the correct etchant? Yes, any answers? Are you getting me?
So actually, in between, I missed that what you said because I was not able to hear you. I
Okay,
just heard the question right now, the last one.
okay. Now, like my voice is clear to you?
Yeah, yeah, it's clear. I guess it's problem by my side.
Okay. So, let me draw it again. Okay. So, suppose we want to create a pattern which, like, we have silicon, okay, and above it we have deposited gold, okay, and on top of it we have pattern photoresist. Like, we want to protect these areas, we have put photoresist, okay. Now have an uh, we want to go for wet etching. So we want an etchant. What should be the etchant? Etchant should be able to remove only gold, or it should be able to remove PR, gold, as well as silicon. Which one will be better?
The one which is shown as a PR one, the mask, the pattern that we would
Yes.
like to have. The other thing we should have to remove, right?
Yeah.
So wherever that mask is there,
Mm.
except besides that, the photoresistive material also needs to be each only photoresistive because below that there is a gold. No?
Mm. So we want to pattern the gold according to this, right? We want
Hmm.
this area of
Okay.
gold to be this area of gold to be removed. Okay.
Then yes,
So
gold needs to be removed. Hmm.
gold need to be removed. So
Hmm.
if we have two different type of etchant, one etchant is like it is able to remove only gold and PR will not be affected. Silicon will not be affected. And another etchant we have which will affect PR also as well as silicon a bit along with gold. So which one will you prefer?
The first one because silicon should not be affected. No,
Yes.
here in this case,
So that
would
is the
like to
thing that
retain.
is, yeah, that is the thing that is called as selectivity. So our agent should be highly selective, that it should remove only and only the material that we want to remove, not any other material. So while like there can not be any ideal agent like that, right? So while we are going for such etching processor, generally we see that what are the other layers that are put on our like device. Suppose that we are using something like ZNO, or suppose that you are using something like MOS2 or something. So the etchant you are using should not be affecting that part, right? Suppose you want to remove gold or pattern gold only, so it should not be removing other things. And that is why
Okay.
before going towards etching, we have to take care of these things. That if there is a layer below it, it should not etch that layer also, right? Otherwise, some unwanted patterns will be there. Then is anisotropy. This is something some a very important etching matrix. Isotropic, like etching is generally of two types, isotropic and anisotropic. Isotropic means equal in all directions, like it is etching in all the directions. So if you actually have such opening, so ideally it will try to etch in such a way, circular, right? So this is isotropic. And anisotropic is that it has different rates in lateral and vertical direction. So either it will etch something like this or something like this, or ideally such kind of profile will be formed. Vertical. There is no perfect etching. Always remember that we cannot go for any etchant that will perfectly be vertical. Okay, that is why we need to find out the anisotropy rate. Anisotropy, and anisotropy is defined as A equals to 1 minus RL upon RV. RL is the rate in lateral direction and RV is the rate in the vertical direction, rate of etching in the different direction. For a perfectly anisotropic etching, A should be 1. That means this parameters become 0. No, sorry. Both are same. So it will, if it is RL, that is lateral should be 0, right? RL upon RV, vertical it is whatever rate is there. In lateral direction there is no rate, so it will become 0. So we will get A equals to 1 for anisotropic. Whereas for a perfectly isotropic etching, we will get A equals to 0 because RL equals to RV. Then we have 1 minus 1. That means A equals to 0. Clear till here? Most of the question,
Yes.
most of the questions that are related to this formula one. So we have to keep
Yes.
in mind this one. A
Okay.
equals to 1 minus RL upon RV. Fine. So another term that will come again and again is undercut. Okay. So it is the lateral distance per side under the mask. So the ideal pattern that was expected was this, right? But we have got some extra etching. So this extra part that has been etched out, this is the undercut. Okay. And it will also depend on the isotropy A. Why? Because if it is, yeah, please answer. Hello.
Yeah, yeah, sir.
Yeah. So why will it depend on A? How much undercut is there? Will there be any dependence
Uh,
on A, the parameter A?
because here in that case, anisotropic may will want uh, should that according to the formula, na, what we had seen that should be RL should be 0 actually lateral.
Huh.
But
So if we have more anisotropy, this undercut will be higher or lower?
if we have more,
More like anisot A, the value of A is higher, like say 0.8 or something. Will this undercut, like suppose we have A equals to 0.8 in one case, and in another case, anisotropy is 0.6. In which case the
This is the
undercut
one
will be high. Yes, yeah, please.
point 0.8 and A is point 0.8 and point 0.6 you
6.
said.
हाँ, so
So
in
in case
हाँ,
point 6 में कम होगा sir
yes, so
because
undercut will be less in point
less.
0.8, not point 0.6. More the anisotropy, less will be the undercut, right? A is
Okay, okay.
anisotropy. So more like when it is going towards 1, right? When
Hmm.
anisotropy is 1,
So undercut
the
will be less. Yes, yes, because it is
undercut will be
going towards the perfect one.
perfect one.
Yeah.
Yes. So we have to just understand that whenever we want to find this, uh, like whenever we want any relation, we must understand anisotropy means we want it to be perfectly anisotropic. That is the perfect way. But the problem that happens is that there is never an anisotropic etching. There will be some portion of anisotropy, okay, and that is why this parameter is important. How well it is, like what is the percentage of anisotropy in it, right? There is no perfectly isotropic etching, no perfectly anisotropic etching, right? There is one other important thing in which is also there, and that is orientation selectivity of silicon. So silicon etching generally done using KOH and TMA etching. Okay, so in this case, the density of planes differs. If you go into that unique cubic cell and all, you will find that for different planes like 111, 110, 111, 100, you must remember, you must be remembering that in our first class, we talked about different orientation of wafer. When you see a wafer, how will you find out it is 111, 110, or 100, right? Do you remember that?
Yes, sir, somewhat.
Okay.
Because I have not attended that first initial 4 5
Okay.
sessions, but just
Mhm.
go through.
Okay, not an issue. I will be covering that part a bit today, like when we will
Okay.
be revising. Today, like we will be revising the whole thing in a very short and crisp thing, so that
Yeah.
you remember all the
Okay.
things. Okay. So it is found
Yeah.
that density of planes 111 is higher than 110 and 100, and that is why the H rate of 111 plane in case of KOH etching is very slow compared to 110 and 100 plane. So suppose you are taking a wafer 100, that is the general one, 100 wafer. It will start etching when put in QH, but it will stop when it finds the 111 plane. Okay, that is like uh, it acts as a etch stop layer. In some cases, etch stop is also put purposefully, like by doping some material which will stop the etching. Because same material we want to stop at one point, silicon, but we don't want to go below a layer. In such cases, sometimes at that depth, ion implantation is done. But one of the best way is that it actually itself stops when it finds the 111 direction, because it's very slow in that direction, and it is reaction rate limited, and this is widely used in case of MEMS. Only the problem is that a slanted kind of structure will be formed instead of what we wanted, but it is better than a circular, like a circular structure. uh, Compared to a circular structure, this one is much better, and we already know,
Yeah.
so such compensation can be done. Yes,
I said
your
okay, sir. Okay.
okay. So what happens is that this is the 111 plane, and this makes an angle of 54.74 degrees with respect to 100 plane. Okay, and this is where the etching stops. So we have, if we created, ideally what we wanted was some a pattern like this, but we are getting a pattern like this, and gradually it will move, like it will be a pattern like this, but whatever will be the pattern, it will be at the same angle. Okay, if we keep it for more time, the depth will increase and we will get a pattern, but the angle between the top layer and this slanted wall will remain the same, 54.74 degrees Celsius. And that is one other important parameter from which questions are generally asked, right? So based on this, now let's solve these problems. We have already solved this in previous classes, uh, but now, and that is why I will expect that you try to solve this at first, then I will assist you like what is the correct way. Fine.
Okay.
Yeah. So it says a layer of silicon dioxide of 0.5 micrometer is deposited on a silicon wafer. So we have a silicon wafer and we have SiO2. Okay, and this is 1.5 micrometer. Okay, it is patterned with circular structures. So on top of it, some circular structure are kept open, other is covered. Okay, so suppose that these are circular openings, and the diameter of this is 20 micrometer. After development, it is dipped in HF for 1 minute 30 seconds. Okay, so after it was dipped in HF, that will remove SiO2. It for 1 minute 30 seconds. It is found that what the structure should have been, the depth is, we are finding the depth till here, it is 1.3 micrometer. So it has not reached to the end yet. And what was expected was 20 micrometer should be the pattern, but we got it 21 micrometer. What is the anisotropy of this etching process? So how will you calculate it? Yes, and like any answers?
Yes, I'm just 8 minutes.
Yeah, sure.
So we have to use that formula only, the 1 minus
Yeah,
RL by RB.
yeah. So here we don't know the rate, so we can also rate will actually be proportional to the actual lateral or vertical depth. Okay, so we can say that uh, A can also be given as A minus L upon D. L is the lateral, D is the depth. Fine. So you can use this formula also.
Okay. Okay. So I'm length. So 1 micrometer difference is there because we want the 20 micrometer is required, and here we are getting it as 21,
Mhm.
which is distance is also in this case 1.5 micrometer, but we want it as 1.3. So point
We, yeah, we
two.
are getting 1.3 only. Yeah. So what will be the answer?
Is it point 0.8?
0.8.
I'm not
Like,
so sure. Sorry. No, here the options are given.
Mm,
Yeah, 0.841 is there, but just
okay.
quickly calculated, it is 0.8.
So what are you using? 1 minus. So what are you putting as L
L,
here?
I'm taking it as point 0.2
Point 0.2.
difference.
Why? Lateral, that means
Because
the
the
horizontal, the extra horizontal we are getting. So L is ideally the undercut,
undercut. Okay.
I, and D is the depth.
So D is
Okay,
the depth. Okay. Okay. Okay.
okay.
Then in that,
Mm.
then I,
Yes, continue.
is it 1.2? No, some
No,
confusion.
let's not get to answers directly. Let's do it
Uh,
step by step.
okay.
So what is
So
the
L as
value?
the, huh,
Yeah.
as L is this na the horizontal one. So it is 21 minus 20 micrometers. So it will be the difference is 1 micrometer.
Mm-hmm.
And while the depth, so it is a 1.5 micrometer, right? And we want it as 1.3. So 1.3 minus 1.5. Yeah, 1 point
What is the use of 1.5 here? Depth is the depth of the profile. That is the
profile.
etching
Okay.
profile. So 1.5 have no role here because it
Okay.
has
Okay.
not got
Then it is
that
a
is
1.3 only.
1.3 only, right? One more thing
Hmm.
is that if you see this, let me go to the next slide. Yeah, if you see this one, okay. So
Hmm.
ideally this was 20 micrometer,
Hmm.
right?
Hmm.
But we actually
Hmm.
got it to be 21 micrometer,
Hmm. Hmm.
right? So if we
Hmm.
see it like this, so this is like this, right? This is the profile. The
Hmm.
mask is still here, okay? So
Hmm.
this is 20. So what is
Yes.
this? What is the undercut? Since the undercut is both sides,
Point
this is
five.
20.
Point five.
Yeah, so it is zero point 0.5
Point five. Huh.
because it is divided on both the sides. And that is
Yes. Yes.
and this depth is 1.3. So sometimes in questions, a lot of information is given. It is not necessary to be used,
Okay.
right?
Okay.
Like 1.5, and that thing is not necessary. If this
Hmm.
profile would have reached something beyond 1.5, then we would have to take in account silicon and other things, right? So
Okay.
this is
Okay.
simply so L becomes 0.5 micrometer and D becomes how much? 1.3 micrometer. So if we do 0.5 upon 1.3, what will we get?
Yeah, I'll just do that calculation.
In exam, I think scientific calculator will be provided. You cannot
That
take
will be
physical.
provided. That is what, yes, it's mentioned.
Uh,
Sorry.
yeah.
Yeah, I'll ask some questions about it because I'm giving it the NPTEL exam first time. So I'm not aware of what exactly the
I think
soft.
they give, yeah, they give a mock interface for you to practice before going to exam. So you can
Okay.
try that.
Okay. 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 I
So if we do like this, 0.615, right? Am I correct?
Yes, yes. Sorry, I was on a mute. I was talking that yes, it is.
Okay,
I'm also getting point three. Sorry, sorry.
okay. So now this we are clear, right?
Okay, understood. Okay,
So it is 615. Now,
okay, okay.
next thing. First, one very important, like there are three important things that will keep on coming. Like one thing
Hmm.
was it, this anisotropy, second was selectivity, H selectivity, and third is
Hmm.
where it stops like 111 and the angle 54.7. That you
Seven.
have to, yeah, that you have to keep in mind.
Okay,
Okay,
okay.
okay. Now, here the question is, a layer of 1 micrometer thick SiO2 is deposited on silicon wafer. So very
Second
similar to the
vector.
previous one. So
Hmm.
silicon, and then silicon wafer is there, and
Hmm.
uh, this thickness is
Let's have a-
1 micrometer, right?
1 micrometer.
Again, it is patterned
Deep
like the
temperature.
previous questions and dipped in HF. Okay. After etching, now here the question slightly changes.
Hmm.
After
Hmm.
after this, we found that actually 100 nanometer of silicon is also etched
Each.
along
Okay,
with
which you
silicon
undesired.
deposition.
Okay,
Yeah.
okay.
So this pattern, like in the previous case, it was not going beyond this, but in this case, it is going beyond this. It is
Yes,
even removing this area.
that is 100 nanometer.
Yeah, 100 nanometer of this. So it is not much, but it is actually removing.
Hmm.
Okay.
Hmm.
What
Hmm.
is the selectivity of HF to its SiO2 when silicon is considered H stop layer? So what is the selectivity?
Selectivity. Okay.
Yeah. So how much selectivity?
So now selectivity form. Just now you said that it is the ratio of
Hmm,
each rate of one material to the another material.
another material, right?
But here
So
it is given.
so let's say directly saying like this will be, it is saying that it shows is also edged. So it is not saying that inside the profile it is edged. So let's say that from the back it removed 100 nanometer. Okay. In the meantime, in the because the whole thing is dipped, right? So it
Hmm.
removed
Hmm.
100 nanometer from here, right? So
Hmm.
while it removed this 1 micrometer, it removed 100 nanometer from silicon. Then what will be the H rate? What will be the selectivity?
Then 100 is to 1
1 micrometer if okay, sorry,
and 100 nanometers.
yeah, yeah, and 100 nanometer. This is the ratio of
So,
etching, right?
sorry, हाँ, micrometer में है and it's in nanometer.
Yes. So it will be
Hmm.
three zeros,
Yes.
right? Nano to micro, yeah, three zeros. No, so why am I putting?
10 raised to minus 6 it will be.
Okay, let's directly convert it into powers and all. 1 into 10 to the power minus 6 and 100 into
This.
10 to the power minus 9,
Hmm.
right?
Hmm.
So minus 6 cancels. So 1 upon 100 into 10 to the power minus 3, right?
Hmm.
So 1 upon 0.1, that is 10 upon 1.
So 10 is to 1.
10 is to 1, right?
Hmm.
Am I doing the correct calculation?
That why it is not 100 nanometer to 1 micrometer?
Because it is saying that
Like
what is the selectivity of HF to
it chip
HSiO2.
to each SiO2. Okay, okay,
Okay.
okay.
When considered, so whatever we want with respect to whatever. is there. So
Hmm. Hmm. Hmm.
when con
Hmm.
when Si is considered H stop layer. Okay, so it will depend on the question. If it was the opposite, if it was what is
Opposite.
the Si with respect to SiO2, then it would have been 1 is to 10.
10 to 100. 1 is
Okay,
to?
then it would have been 1 is to 10. Like if it was for silicon, if the
Okay.
selectivity of silicon is required, in that case it will be 1 to 10. Here it is of SiO2, so it is 10 is to. Fine.
Sorry, selectivity of SiO2 to silicon, if it is there, then it is 10 is to 1. Just now we had calculated. And
Yes,
if it is exactly opposite, then it will be 1 is to 10.
1 is
Okay.
to
Okay.
10. Yeah,
Huh.
exactly the
Okay.
opposite of this.
Yes.
Yeah. So it is 10 is to 1. Yeah.
Okay. Okay.
Now let's find this out. It is showing the anisotropy of the eventual profile after the process shown in the figure is carried out is equal to what?
Hmm.
So a
Hmm.
mask of 5
Eventually.
micrometer was made, and
Hmm.
finally we are
Hmm.
getting 6 micrometer, and the depth is of 2 micrometer.
So
So what is the
micrometer.
anisotropy?
It is the same way the way we calculated in the first example.
Yes,
S- So then in this case it will be
zero
point 0.5.
point 0.5 in this case, fine. 0.5 will be L, and D will
No.
be
Yeah, yeah.
what?
Zero point 0.5 by 2 micrometer. No, it is.
Yes, by 2 micrometer. This is also micrometer. So,
So 1 minus zero point 0.5 by 2.
mhm. So what will be the result?
Mm, 0.5 by
1 minus 0.5 by 2 equals to 1 minus 0.25 to 0.75, right?
Hmm.
Okay. Clear?
Hmm.
Now,
Yes.
now, now you have got, like it is simply for just we have to
Okay. Okay.
uh,
Understood. Hmm.
just we have to take care that we are finding the L and D correct. If it is there, it is
Hmm.
very simple.
Hmm.
Directly you put the value.
Okay.
Now let's come
Okay.
to
Okay.
the next part where both the
Okay.
things are getting edged. The
Okay.
anisotropy of here, anisotropy is already given. A
Hmm.
is
Hmm.
already
It's
given. It
point
is
0.5.
saying
A is
A
given.
A of SiO2 is given. So
A
this is
is S.
SiO2, SiO2,
Hmm.
and A is
Hmm.
given as 0.5. Okay.
Hmm. Hmm.
So
Give.
now the final schematic we are getting, and the depth, the extra depth that is inside the silicon that is happening,
Hmm. Hmm.
that is given as zero point 0.1 micrometer. So
Okay.
what is the thickness of this SiO2 layer? This is the question. So
Okay.
the
Okay.
same
Now it
formula in
is.
different way.
Okay.
Yeah.
Okay. Earlier that was given and
Mm.
understood. So now in this case, L is
So I
given
will.
as 1. 1.
L is uh, not given as a one. L is the yeah, L, fine. You can, but see here.
1 micrometer and
See
just one second. 1
this.
micrometer and this total, matlab x plus zero point 0.1 micrometer is there, something is there.
Mhm,
A is equal to 1 minus 1 micrometer divided by x plus 0.25.
mhm.
And here it is zero point 0.5. So zero point 0.5 times x plus zero point 0.5 into
If I,
0.25.
yeah, I'll put it like this. Yeah.
So is it one big
Uh, Take care of this part also. This is
point two
0.25,
five?
0.25
Okay,
extra. So because while etching this silicon, this SiO2 will also be etched extra, right? So that also we have to take care of. And that extra SiO2 etching is of 0.25.
Okay. हाँ sir, so what I have written here, A is equal to, मतलब A is given as 0.5, so 0.5 it is equal to 1 minus, right?
One, yeah.
And this uh,
L
1
will,
plus 0.25, it will be 1 plus 0.25.
or 1 minus
No, no, no,
0.25.
no. It will be 1, L is
One is,
1, right?
no, L here. See, if we just take the undercut for SiO2, it is this part only.
It is 1. Okay.
It is 0.25 less than 1. 1 is the total undercut.
0.25 less than 1. Okay.
Yeah,
Yes, sir. Yes, sir. Understood.
it it is for SiO2 and silicon both. Now we just want to find out for silicon dioxide. That is why we will have to
Silicon
remove that
dioxide.
silicon part. Yeah, for SiO2, since this is SiO2, right?
Hmm.
We want to
Hmm.
find the depth of SiO2 only. We don't want the
Okay.
silicon. So this extra part we will have to remove. That is because of the silicon etching, the time it is taking to
Hmm.
etch out
Hmm.
the silicon,
Hmm. 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 Hmm.
and that is why we will have to remove that part.
Okay. Okay. Then in
So
that case, it will be
1 minus
oh,
0.25, right?
yes.
So now if you solve this, what comes? 0.75 d equals to 0.5. So d equals to 5 into 0.5 equals to, okay, it will be 1.25, I think.
Hmm.
I'm not sure about the calculation, just check once.
Just
Not
I
1
just got
point,
1.25.
1.25, 75, no,
1
1.5,
minus
no?
0.25,
Yeah,
0.7.
1.5.
0.75.
Yeah, yeah. Like 75, yeah, 1.5.
But that will be 1 minus.
Which one?
So D will be 1 point. Sorry, what you are calculating? 0.7.
D is the depth of the silicon dioxide
Depth
I'm
of.
taking.
Hmm. Hmm. Hmm.
Yeah,
Hmm. Hmm.
this
Hmm.
one D. Fine, or
Hmm.
some confusion
Yes,
in
yes.
this.
No, no, no,
Okay,
no.
okay.
That only I have to, again, just I have to read the question and I have to
Yes,
see this diagram.
see,
I'll
yeah.
just revise it
So
afterwards.
this, so I have put maximum questions that we have done, and if you are not very confident in this part, just practice. It is just one formula. That is all, nothing else.
Hmm. Hmm. Hmm.
Right. So just
Okay,
practice
okay.
two, three times. You will be able to do it.
Yeah, yeah.
Okay. Now comes the next part. That is where H stop of 111 is used. So it is said that a square mask with dimension 10 micrometers is aligned such that one of its sides is along the wafer flat of 100. Okay. So
Mm-hmm.
if the wafer direction is, and how we find the wafer flat? Like if you have this wafer, the primary flat, yeah, the cut,
Primary fluctuates.
yeah, that is the direction of the wafer. So mask we are using such that it is aligned with this. So this direction is 100.
Mm-hmm.
Okay,
Hmm.
and the distance is 10 micrometer. Okay, so
Yes.
now the K, so overall, what will be the area that is expected? 10 by 10, that is 100 micrometer square, right? This is the area of the opening that we are keeping. But when we are doing the KOHH, finally, whatever the square pit that will form, what will be the area of that?
No idea, sir.
No
Sorry.
idea.
Actually, I stuck at this formula and all those things, or this part particularly itching, how to calculate it. That's what
Calculate.
asked you to
Okay.
revise it.
Yeah. So uh, let's say that this is 10 micrometer. Okay.
Okay.
This is 10 micrometer, right? And this is 10. But this is in the 100 direction, right? Now we already know that what is the direction of the stopping, that is 10
One, one,
111
one,
111.
one, one.
So it will be something like this. Okay, so whatever will be the final profile, if we just keep it inside, we will get a profile like this, right?
Hmm.
Because it will automatically stop at 111. So this is 111.
Hmm.
So this, now the area that was this has increased, and this is
Hmm.
the
Hmm.
area. So we want to find out this area. So ideally we have to find the increase in this. So this is 10 micrometer. So simple
Hmm.
trigonometry if we use,
Hmm.
okay, and
Hmm.
if we divide it like this, right? So what is this angle?
Which one?
This one,
Okay.
this angle.
There.
Yeah,
Just 54.74. You said just now with the.
that is
No, that
between,
was the top ladder with the. Yeah, yeah.
yeah, that
This
is
is
the profile. So this, if we
profile. Yes, yes.
calculate, yeah, if we calculate this, the angle will be actually 45 degree.
Hmm.
Okay.
Hmm.
So now in this triangle, this is half, right? So this is 5 micrometer,
Hmm.
this part. We want to find out
Hmm.
this one. And actually this is half of the total. If we draw it properly, like since this will also be equal, this will be equal, right? These two will be equal. So what if we find this, should I use some other color, I think. If we find out this part, right? So the side will become just the two two times of this. If this is x, 2x will be the total side. Am
Hmm.
I correct? Right. So now
Hmm. Hmm.
this angle we already know. So this, if we rotate it like, or to see it properly, if we draw it here, okay, this is the, this is a right angle triangle, 45 degree. So
Hmm.
I just, this is the hypotenuse h which we
Yes.
want to find. This
Okay.
base
Okay.
we already know, that is 5,
5.
5, right? Because it is half of the 10. So
Yes.
what
5.
relation can we use? Sine, cos, or tan? Hypotenuse by base, that is
10
cos,
will be there.
yeah, cos theta equals
So,
to uh, base by hypotenuse, right? B by
hmm.
h. So cos 45 degree is equal to, base here is 5,
This is 5.
and
Hmm.
h we don't know.
We
And
would like to find.
yeah, cos 45 is 1 upon root 2 to 5 upon h. So h equals to 5 root 2.
Point 0.7 my 1 by point 0.7.
No, let's not go in decimals. Okay,
Okay, okay. Okay.
let's not put that decimal part. Now,
Okay.
because here, just keep in mind, when we have to deal with, when we have to square something, don't put the value of under root 2. Anyway, that will
Mm-hmm.
get squared because sides have to be squared. So what will be the side? Now the side will be 2 times of h, that is 10 under root 2, and area will be side square is equal to 100 into 2 is equal 10 square, 2 square, under root 2 square. Fine till here. So it will be 200 micrometer.
200 micrometer square.
Yeah. If we put the root 2 and then we'll have to do extra calculation
Then,
with it.
yeah, okay.
Okay. Is it clear? I think this is the part where you were stuck like
Yeah,
earlier
because
also.
I had not attended and was not
Mhm.
so conversant.
Yeah,
Okay, understood.
understood, right? Right. So, okay. So
So such
200
kind of
micrometer.
numericals will also be there, na? So in
Yeah,
that
it's
case.
such numerical part is just this much, I think. Nothing else is there in numerical. Okay. Now,
Okay.
in short, let's see the whole process we have studied.
Okay.
Fine. So, in general, if we have to make a chip, okay, that will contain a lot of these processes repeatedly, okay, but these are the basic steps that will be there. We start with silicon wafer, okay, and how do we find that which kind of silicon wafer it is? It is based on primary flat and secondary flat.
Yeah.
Fine. So if it is n type, it will have 100 n type, it will have primary and secondary flat at 180 degrees Celsius. If it is p type, it will have primary and secondary flats at 90 degrees Celsius. Not 90 Celsius, 90 degrees, the angle of 90 degrees. Whereas in case of 111 n type, it will be like adjacent to each other. And in case of 111 p type, it is single flat, nothing else. Fine. And someone, I think, asked, what about intrinsic? Any
Hmm. Hmm.
guesses? Intrinsic,
Hmm.
like we generally don't buy intrinsic wafers. I have,
Hmm. Hmm.
like, I have not seen because I think that is a bit difficult to manufacture. And if you read the FZ and CZ processes, you'll find that actually
Hmm.
doping is done while making it only.
Okay.
Okay, so and if it is there, I think that will have no flats at all. But
Hmm.
I have not seen intrinsic wafer. Okay,
Okay.
so second thing is we have read about cleaning, that is RCA1, RCA2, Piranha, right? These are the cleaning processes. Oxidation, we had wet and dry oxidation,
RCA
right?
long form, what have you told that? I just forgot it. You mentioned that RCA some long form.
Yeah, RCA is Radio Corporation of America, and that is why it is even known as SC1 and SC2, that is Standard Cleaning 1 and
Ah,
Standard
ah,
Cleaning 2. RCA was where it was developed in Radio Corporation of America, and that is why it
okay.
is even called as RCA1, RCA2. Now people use SC1, SC2. These terms are also used.
SC2. Okay.
Yeah.
Okay. Okay.
Then we read about oxidation, that includes wet
Hmm.
oxidation and dry oxidation. Uh,
Hmm.
which one is better, wet or dry?
Hmm.
Which one is faster?
Weight oxidation.
Wet oxidation is faster. Okay,
Better
faster.
also.
But dry oxidation have better film quality because
Okay.
uh, hydrogen is released in case of wet oxidation, that actually
Mm-hmm.
when it
Fluid.
comes out it deforms the
Yeah.
surface.
Okay.
Then we talked about metal or film deposition, which have PVD and CVD. We discussed CVD in details in the last class, right?
Hmm.
And PVD, that includes thermal sputtering and these things. Then we have
Hmm.
learned about lithography, that have processes like spin coating, soft bake, exposure, develop, and hard bake, as well as for negative photoresist SU8 and these things. It can vary. Okay, like hard bake will be before developing and these things. Just make a flow chart of all these different
Yeah.
processes. It will be very easy for you to remember,
So
like
that photo
keep it.
register that one material was there, na S1813.
Yeah,
So what is that number? 1.3 and 1.8. 1.8 is 1.3 is about the thickness, if I'm not
Hmm.
without that one.
Yeah.
But it is 0.13 micrometers.
Yes.
Is it
It is 1.3 micrometer. No, it is, I
1.3?
think, opposite.
0.1.
One, no, 1.3 will be like when we do it at around 4,000 RPM, we get 1.4, right? So it cannot be like this. No, it must be the opposite. I think at
Point.
1300 RPM, I will have to check. I
Okay.
know two, three values. Like when we do it at 2000 RPM, we are getting around 2 micrometer. At
Sir,
4000
I just
RPM,
asked you the doubt because I have noted down at the end of the session, you continue with your flow so that I'll
mhm,
not disturb whatever you are.
yeah. I think there are some values. You will get a chart why it is 1813. Like there are at different RPMs, you will get different. Okay. Then we have talked about, we know about dry etching and wet etching. We talked about wet etching in this anisotropy and anisotropy, selectivity, and this orientation etch stop. These things are important. Etch
Okay.
stop. Fine. And then at last, PR is removed using acetone or stripper. And this is the general flow. And these things are repeated again and again. Sometimes in case of this transistors, 200, 300 levels of lithography are done, one over another. Okay. So let's revise quickly. What is RCA1? What is RCA2? Okay. And what is used? RCA1 is, like I said, process developed by W. Kern while working in Radio Corporation of America, from where the term RCA comes. It is a mixture of ammonium peroxide mixture, which is actually operated at 80 degrees Celsius. It is used to remove particles and polymeric materials. Okay, and it makes the surface hydrophilic. Water will get attracted to it. And then the next process is hydrochloric hydrogen chloride peroxide mixture. HCl H2O2 H2O in 1:1:6 ratio. This is also done at 80 degrees Celsius, and it removes metal contamination if there it is there, and it makes the surface hydrophilic. No, is it the same? No, it should be
Yes, sir, it
hydro.
is same.
No, this,
One is phobic and
yeah, no, this, yeah, metal contamination. This will make it hydrophobic. Okay. At last, when you remove, once it is clean, if you see the wafer, water will not stick on it. Water will just
okay.
flow with it. Like nothing will stick on it. Okay. Then there is another one, piranha cleaning. Okay. It is used to clean organic residues. Like in general, when we are handling, or maybe like while being transported or something, some organic material like oil kind of residue or such things may stick. Okay. So piranha cleaning is done to remove dirt. In a sense, any dirt, if it has come, any organic biological thing, or suppose that your fingerprint, though it should never come. Okay, such thing, then piranha cleaning is done, and this is one of the very dangerous chemicals, and it was first made to clean these utensils, like when it becomes old and all. So it was this solution was used to clean utensils. It will make it look like new again. Okay, so sulfuric acid and hydrogen peroxide and 3:1 ratio, very corrosive to organic material. So if you put your hand, it will corrode. Okay, and when you mix this, it becomes very hot, and after everything is done, it becomes water kind of, like nothing. Once the reaction is over, it is very normal. Okay, it is named after the piranha fish that can eat like 80 kg of a person can be eaten in 5 minutes by this piranha. Very small fishes they eat. That is why it is named like piranha. So these three are the cleaning processes. Those are commonly talked about. Okay. Then we have talked about oxidation, that is the growth of silicon dioxide using oxidation. And here also one uh, asked now which is better. So here in case of wet oxidation, you see hydrogen is released, yeah, and that will actually make the this film quality lower compared to dry oxidation, and that is why uh, it is fast. It is much faster compared to dry oxidation, but the problem is that it will not be of good quality. So generally, what is done is that dry, wet, dry is used, because on the top we want good structure because other structures will be made above it, and at the bottom where the interface is there with a silicon, there also we want good addition and good quality of paper. So dry, wet, dry, such a process is used. Then one very important part that was uh, like some numerical can come from here also, that is how much of silicon is used to make silicon dioxide. Okay, so if you do some like volumetric as well as atomic mass calculation, you will see Si and SiO2, like O2 is 16 plus 16, right? It
32.
atom, yeah, 32, and Si I think 35. I forgot the exact value,
Okay.
35.5 maybe. I'm not exactly remembering the value. So if you do the calculation, you will find that actually this SiO2 and Si, the ratio is something like this. Yeah, 44% of uh, Si, well, like 44%. If we have suppose not if suppose we are making 1 micrometer SiO2, for that you should have used 0.44 micrometer silicon. Okay, so there is an increase of 56%. Fine.
Okay.
So based on this, some calculations can be there, and this 56% of SiO2, the total layer that will form, 44% of it will come directly from silicon, and the rest is like 44% of silicon layer has been utilized. So if you start from suppose you have a silicon wafer like this, if you grow it, it will actually grow up,
Hmm.
consuming some part of this and going beyond it. Okay, so it will be 2.27 times the SiO2 layer will be 2.27 times more than the Si. So if 1 micrometer, like if we talk it in reverse order, if 1 micrometer
Hmm.
of silicon is used, 2.27 micrometer of SiO2 will be grown. Fine.
Mm-hmm.
This is another thing where I think 1, 2 numericals were there in assignments also. So you can try to
Yeah.
revise those. So next is the physical vapor deposition. We have seen like there are some techniques like thermal evaporation, sputtering, ion plating and cluster deposition, laser ablation, aerosol deposition. These were not covered much in this lecture, though I have just put it, like I have a table, so I put it. So what kind of materials? Thermal evaporation. Here you are evaporating the material using very high current. Okay, uh, so like at a very high vacuum, you are evaporating it and depositing it. So certainly here non-metals not possible. Some metals are possible. Coating adhesion is not very good as compared to other processes. Okay, but it is you can say a bit cheaper than other processes like sputtering and ion implantation. Okay, so most common use, but it has the problem that it cannot deposit your uh, non-metals. Okay, then comes the sputtering, better coating adhesion, then vacuum evaporation or thermal evaporation. Can coat compounds also like Al2O3 and others. But the problem is that slow deposition rate as well as the deposition rate is not constant. It will vary, and you might not be able to determine, like, suppose based on your unitary method, we did that in 30 minutes, 50 nanometer is being deposited. So I will run it for 1 hour and I will get 100 nanometer. It may vary. We may get 80 nanometer only, or we may get 120 nanometer. So rate control is a bit difficult in case of sputtering. Okay, but here again there are two sources. Here plasma, along with this plasma, argon plasma is used. Okay, so uh, it can be RF and DC, both systems are there, and combination of these two are also used. So uh, this is the like thermal evaporation is there, or sputtering we can go for. Then ion implantation, like you just go through it. This is just for extra thing. Okay, that will not be part of the course. Okay,
Okay.
so that's all. And I think one, okay, not there. I think one other slide I have put that I cannot put here because that is a video. Okay, just a minute. I will open that and say for lithography I have put one different slide. Okay. Mhm. Just a minute. I think it has some videos, so it will take a bit of time.
Okay,
So yeah, so it will take a bit of time to open. Okay. And that, like, the whole process we already know, just to have a revision. Okay. In the meantime, you can ask some questions if you have some questions. Like,
so just now we discussed the thickness of silicon consumed. Na? So
mhm.
if I need to calculate thickness of silicon consumed, then can I take directly that ratio as 0.46 or 0.44 multiplied by the thickness of the oxide film?
Yes, yes. Then we will get the used one.
Get the correct one. Na?
Yeah.
Okay.
Huh.
And so another one, the
Mhm.
what are these ratios? Na? Like you just say that this should be in this proportion or at this temperature and speed. So those things also we need to be like remember, right? Because those must
Yeah.
maybe asked because for different process there are
Mhm.
different temperature as well as ratios are also to be maintained.
Yeah. Ratio of what you are talking about.
Means just now as we said that in case of cleaning RCA cleaning also that the
I
mat
think that ratio, like, just know the chemicals. Like, these are
okay.
some things. These are things like what I also generally do is that when we have to do, we cross check it. It is not always done like
Okay.
remembering the things. Though while working, you will remember
Right.
the things. Anyway, that will
Yeah.
get remembered in your mind. But you don't need to
Mm.
remember these things. These are something like you will, uh, once you
Okay.
start practicing, anyway, you have to always refer, like in
Correct.
electronics
Correct.
and these things, we mostly refer to data sheets and this before working
Mhm.
anything,
Okay.
right?
And so one more just
Mm.
clarification I would like to have
Huh,
that the one more problem solving sessions where there
huh.
on Saturdays.
Yeah, yeah.
So was this like the content for both the sessions are same, or is was it different? So is there any another like a link to, or the you somewhere I can refer that those sessions also?
I
Any
think
idea, sir?
that is in the same seat we are putting. That is another TA. In the same Google Sheet, you will find both his lectures and drive.
Google Sheets are where exactly the Google Sheet? I'm not able to get that Google Sheet. Where?
If you open your this NPTEL dashboard,
NPTEL course outline. Na? Huh, okay.
yeah,
So
at the bottom of it there will be this something like
okay.
lecture, interactive session or
Okay.
something written like that.
Okay. Okay. Okay.
Uh,
Okay. Okay,
there
sir.
you will
I'll
find it.
just.
Yeah, you can
Okay.
open it, and if you cannot find, you just share the
I'll drop that. Yes, sir.
yeah.
Yeah. And is there any Telegram group for this?
No, no.
I was just asking at the last moment,
Yeah.
but I didn't.
No, no group. Like
Okay.
this is something we just have to take the classes and we have to put the videos and slides.
Yeah.
So we are
Yeah.
putting that, and we are a bit free to put questions, though the content is almost similar. Like you can say that we are putting similar questions since we
Okay.
are putting it
Okay.
from the source. But yes,
Hmm.
it is uh, like how much questions you are taking and all that can differ a bit. So I think the
Hmm.
contents will
Hmm.
be
Hmm.
similar only, not much
Okay.
difference.
Okay.
But you can refer
Okay.
to both. There will be an Excel sheet, everything will be
Okay. I'll just verify, sir. That I'll just go
there.
through that course. Thank you, sir, for just matlab, like for solving my doubts. And
Yeah,
now I'm little bit relaxed or relieved, you can say, because if such kind of numericals will be asked, then I can give a
yeah,
try to those.
yeah. These are not tough, like very simple.
Not
Like
tough, yes, but
yeah,
that concept was itself. I just miss those sessions also from like videos also. Anyhow, I could not
mhm,
manage that. It's my from my side only. I could not, and I had not
yeah,
attended your problem solving sessions also during that week.
yeah.
So little
Not
bit.
an issue.
Yeah.
I
Yes,
think
sir.
it is.
Thank you so much.
Yeah, it is too big a slide that it is still loading
It
only.
is not open now.
Yeah,
Okay.
I think it is just 75% done. So let's wait for
Okay.
some time. Yeah.
Yes. Sure.
So you found that link.
Not it right because I'm attending it from mobile na,
Okay,
and
okay. So I
uh,
will just put. I think. mm, I think I can copy the link and put in the chat maybe. Yeah. This is the Excel sheet link that you will find in the course.
okay.
Also, course dashboard also. It's the same
Okay.
link. Here, both of us are putting the this putting the links of slides and all. So I think
Okay.
that will be fine for you.
I'll just copy this link so that I'm not able to copy. It is going to that Google Sheet directly.
Okay. So here you will find all my lectures as well as if Udipta is there. His lectures will be
So that is for just to get a practice for a practice. If different questions are there, then that will help
there. Yeah.
to
Yeah.
that.
Mostly
That
they will be similar questions only.
okay.
But
Okay.
yeah, some questions can be different. So you can take all.
Okay.
Like if you have any differences, you can utilize, like you can practice that also. That will be,
For practice purpose only, actually, I
yeah,
asked.
that will be much
Well, I've
easier. Yeah.
attended your sessions. In between, I've tried, but anyhow, something I just have to leave that those meetings also. In the last two meetings, I've tried to attend, but I could not.
Sure.
So I have this time is preferred Tuesdays. So I'm
Yeah,
attending your sessions.
not an issue. Yeah, I think it has opened. Yeah. Yeah. So, okay. This is actually how, what is actually lithography. To understand it, it
Okay.
is something very similar to this. Like you see one pattern, then
Mhm.
another pattern, and they are made using this. If you see on the top, there are some marks, alignment
Yes,
marks,
yes.
right? That is
Alignment marks.
very similar to this. Lithography is there, right?
Okay.
So,
Okay.
and you see how multiple layers of lithography are
Yeah.
there just to create the, like what was being done here. A very similar process is there, but in smaller scale. So you see lithography.
Mm-hmm.
That is why lithography, even in 3D printing, they are calling it as lithography, right?
Mm-hmm.
Stereolithography, though it is at
Studio
bigger scale.
lithography.
Yeah, it is
Mm.
at bigger. So this is a very common term. It is used in PCB manufacturing and lot. But
Mm.
photolithography and this, if you say FESM based, electron electron beam lithography and all, these are at a very small level, right? And that is the reason the slides are changing. Yeah. So mostly like they are divided into photolithography and electron beam lithography in case of microfabrication, right? So
Okay.
photolithography, if we put, so the process is like first the substrate is prepared, then
Time to come to prepare one structure or one
yes,
sensor
yeah, one
fabrication for that.
one layer of like to create one sensor or one whole device, we may have to
Hmm.
go multiple lithography. We may have to do multiple
Yes, yes.
lithography, multiple
Mm.
depositions. This is
Yes.
like one set of processes, and this is very common for all. Like the process is
Mm.
similar,
Mm.
the mask will
Mm.
differ. You have to
Mm.
align and all.
Mm.
Okay, so
Mm. Mm.
the process involves like preparing the substrate, applying the photoresist, exposing the photoresist to light.
Mm.
It can be negative or positive depending on the. There will be some questions like this also, maybe that if you are
Bright
using
mark
yeah, positive, then which part will soften, which part will remain,
will be
then
different. Mm.
bright field and dark field.
Mm.
Okay, such things you
Mm.
just
Mm.
revise. I think we
Yeah,
have
device.
covered this. Yeah.
Yes, 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 yes. I have
Then is,
attended those.
yeah, then developing the photoresist, etching the substrate, and removing photoresist.
Mm.
This is the
Mm. Mm.
process.
Mm.
So
Process.
yeah, so if we see like how this, if you see the video, this video is
Mm.
showing for you.
Mm.
If you see the video, like how these masks are designed, it is a CAD kind of software, right? And this is
Mm-hmm.
a simple mask, right?
Mm.
That is used for the photolithography.
Mm-hmm.
A mask kind
Mm-hmm.
of structure that will differ, like what structure you want to make, that will differ according to that, right? But
Mm-hmm.
like this is a common mask, glass kind of structure with metal. Metal is there, right? Here you see
So those are the
metal is,
reticles.
yeah, reticles are there. Okay, so how this is photoresist coating is
Mm.
done.
Mm-hmm.
So like you have the wafer, it's not working. Okay,
Mm.
you have the wafer, you
Mm.
pour pour over it, like on the top you see it is being poured and it
Mm-hmm.
is rotated,
Yeah,
so a coat is
wrote
there,
it.
and that coating, like generally 1 to 20 micrometer thickness
Mm.
coating is done. Okay, and then we get
Mm-hmm.
this photo substrate will be there, photoresist will be there, then it is patterned like with such
Mm.
structure machines. Like if you see, it is a video. Oh, yeah, it was a video. Hmm. So this reticle
Okay.
or mask will be put over it. Light will be exposed. I think it is a bit slow. I
Ah,
prepared it for some
yeah,
other
yeah.
class. Yeah. So
Okay.
UV light will be there, and then if you see it, that part. In this case, if we are using positive, so the area
Hmm.
that is exposed will get softened.
Very-
That
Hmm.
yeah, that we will be able to remove in the next. Like here you see this area,
Hmm.
it is softened. Okay.
Hmm.
So when we put it in developer,
Hmm.
this area will remove. This gets removed, and
Hmm.
that pattern
Hmm.
remains. And then
Yes.
after this hard baking is done. So if you see the process, like if you start with a simple wafer, coat it with
Hmm.
gold, like this is coated with gold. Now at the end of this, we are having such patterns, like some patterns are made on it.
Hmm.
So this
Hmm.
is the process of lithography, and they are done in
Hmm.
like yellow rooms.
Cleaning
Yeah.
balloons. Okay.
So they are done. This is a video I think I took from Duke University. Like they have
Okay.
explained it in a very good way. So
Okay.
yeah, you that was there, right? Now you see the wafer is there. It is already
Hmm.
coated with gold.
Hmm.
Now they want to coat it like with photoresist. So it is put on a chuck. This chuck kind of structure. It has vacuum chuck on which it will be put, and it will be sucked by vacuum. So it will be held by vacuum and put there.
Hmm.
And then once you switch on this vacuum, it gets fixed, and then PR will be poured over it. So that is what why I always say like it is very similar to baking and all. Like
Hmm.
making a
Hmm.
cake and all the processes are
Yes.
very similar. Just it is that it is to be done in a specialized room with other like specialized chemicals. Right? So PR is there, and they are just pouring it, and then
Hmm.
once it is
Spread
rotated,
it. Nice.
yeah, it will spread.
Which type of photoresist we want, like whether it is to be fabricated with a positive or negative, how to take a call on that?
It depends on what kind of structures you want, and generally it happens that thickness, thickness as well
Hmm.
as mostly like the process also. In case of negative photoresist, I have seen that the process is a bit complex compared to positive photoresist. But yes,
Hmm.
lift off is much easier in case of negative photoresist, where you
Yeah,
have to.
so generally for negative photoresist and lift off technique is used, right?
Yes, generally, like what we generally use is for lift off, we use negative.
Mm-hmm.
And negative is a bit thicker, I have seen, and that is why
Mm-hmm.
a thicker profile can easily be made using it. And in lift off,
Okay.
thick
Okay.
profile is there. Thick profile is
Okay.
needed, right? So this is, you see, exposure is now being done. Like
Mm-hmm.
if you see slowly, that chuck goes up, and here the light comes and it exposes.
Mm-hmm.
The whole area is exposed with UV, and then like you should not see this directly
Yes. Yeah.
with naked
Cover.
eyes. Yeah, and then it is developed. Developing is like just like earlier reels were developed, camera reels.
Mm-hmm. Photos.
Uh,
Mm-hmm.
yeah, very similar to that. It is put in a solution, developer solution, and it is kept there for fixed time. It will all the pattern will be visible with your eyes.
Mm-hmm.
If you just shake it, like you'll see in some time everything will come out, and you will be left with just a wafer, which you have to wash, not with running like not with city water. You have to wash with DI water, and then
Yeah,
you see
nice
the
one.
pattern. Yeah, the pattern is
Hmm.
there. And if you check under microscope, you will be able to see, like, generally after every step, inspection is done so that we can see whether the pattern is actually made there or not. Fine. So next comes etching. We have learned about that, right?
Yes, yes,
So
yes, yes.
yeah, I think okay. So that's all till here. Just a revision of all the processes we have learned till now. Okay.
Yes,
So
yes, sir.
any questions or any doubts?
No, not right now. I asked and most of the questions which I had a doubt, particularly, so that you have covered, sir.
Yeah, sure. So that's all. Thank you and best of luck for your
Yeah.